techniques. We have a little like timeline of history of TOC analysis. Fundamentals of TOC, the description of the TOC techniques. We have high temperature combustion TOC, heated persulfate with NDAR detection. There's also UV persulfate with NDAR conductivity and membrane conductivity. And then also touch a little bit on applications and limitations of some of these techniques. TOC analysis is very important. It's a water quality parameter that can't be understated. Generally speaking, when you think of contamination water, that contamination is comprised of carbon-containing compounds. And this is true for all applications: ultra pure water, boiler feed or processed water, water for injection, clean in place, in pharmaceutical, drinking water, and wastewater monitoring. In touching again on the importance of it, there is the compliance monitoring. Here in the United States, we have the Environmental Protection Agency. We have contract laboratories running samples. We have municipals, the communities that monitor that. In the United States, there's a call for monitoring total organic carbon. It is required in municipals of populations like higher than 100,000 plus in most cases. They have to monitor it. Either they're doing it in-house or they're sending it to these contract laboratories. There's safety with the Federal Drug Administration, pharmaceutical cleaning validation, food processes, where either looking at the incoming water for organic content or measuring the effluent after the back end of usage of that. There's permitting processes and such. So sort of like as you take in that water source, you have to treat it and put it back the way that found it. There's the process monitoring. There's chemical, petrochemical industries, power, semiconductor, and again, pharmaceutical water for injection. TOC is not regulated, though. There are methods here that are kind of describe it, but it's not like a mandatory regulation. There's EPA method. There's ASTM methods. There's ISO methods for this. There are regulatory agencies, and this would kind of stand here in the United States. There's the Safe Drinking Water Act. There's disinfectant byproduct rule. This again applies to municipals. Here's the MPDS. These are those permits that communities, industries have to follow if they're using any kind of surface water. They again have to treat that. The effluent has to be put back clean. There's RECRA that is monitoring wells and surrounding landfills, contaminated sites. It's used as a more convenient method of determination in COD or BOD, but that does not replace that. If a repeatable relationship can be determined, then TOC can be used to estimate the others with that. Here we'll talk about the oxidation techniques, and then also pop in here a little bit on the history of TOC analyzers. This is like the first of the timeline where back in 1967, Dow Chemical had started to do some work with a device that was at 700 to 900 degrees C combustion by infrared detection. And then in 1969, Earhart developed an analyzer using continuous flow UV persulfate conductivity detection. OI Analytical now part of the Xylem Lab Solutions company, released our first commercial TOC in 1972, and that was a heated persulfate technique. We kind of developed that in line with Texas A&M University and their oceanography department. They were wanted to monitor total organic carbon in seawater. And then in 1984, Cowett improved the Earhart design with the non-dispersive infrared detector, and that's also the detector that we started incorporating into our instrumentation, non-dispersive infrared. In 1988, there was work done by Sugimuro and Suzuki using high temperature oxidative catalytic combustion at 680 degrees C as well. So the oxidation techniques that we have are the high temperature catalytic uh, oxidation. There's also the heated persulfate with NDR detection, and there is UV persulfate with an NDIR detection or direct conductivity and membrane conductivity. And so we'll touch on TOC fundamentals. Every TOC is built upon these building blocks. There's 4 building blocks for these. There's sample introduction. That could be a syringe injection. We happen to use that on both models of the TOC analyzer manufacturer with both the Aurora line and also the 1080 combustion instrument. There is a sample loop and an auto sampler. We use the auto sampler as well. We have a model 1088 that brings the sample up, and then we inject that with the syringe. Oxidation techniques. There's a combustion, heated persulfate, UV persulfate. That is then converted to carbon dioxide, and then it's detected. Either you can do that by non-dispersive infrared detector, membrane conductivity, or conductivity, and ultimately a display where it's a display, printout, computer, and very, very long time ago, a strip chart recorder. So what can you measure? There's TC, the total carbon. This is a measure of all the carbon in the sample. There's total organic carbon, the organic fraction of the sample. There's TIC, the inorganic carbon, and that is determination on where that requires the use of strong acid for conversion to carbon dioxide. That's where we use sodium, we use phosphoric acid. In this case, with our wet oxidation technique. In combustion, we use hydrochloric acid for that. There's NPOC, and that's an organic fraction of the sample that's left in the solution after acidification and subsequent removal of TIC from the sample. This is by far one of the most widely used techniques. NPOC is equivalent to TOC when volatile fraction of the sample is negligible. This is usually the case in most applications. There's POC. This is a measure of the fraction of sample that can be removed by sparging with inert gas. DOC, by regulatory definition, this is a measure of TOC or MPOC after filtration. You also see people mentioning like DOC as well with TOC, kind of see that. And then also to kind of see DOC where people are talking about the seawater application. Uh, NPOC and then TOC by difference and subtraction. And in that mode, TC is measured first, then the TCIC is measured, and subtraction of TIC from TC provides the TC concentration. 2 measurements are required in this mode to perform that subtraction. Uh, what we do is remove the inorganic carbon by acidification. For removal of the TIC, the acidification is required, and there's no exceptions in that. So, say, like for instance, as I mentioned with the wet oxidation, we use phosphoric acid. In combustion, you use hydrochloric acid with our instruments. And then all methods operate by oxidizing the organic carbon to carbon dioxide. Some of the older methods measure the loss of oxidant. However, for a more accurate measurement of carbon, the CO2 generated should be measured. Now, I have a chart here that talks about the typical levels of carbon in water. For groundwater, less than 1 microgram per liter, TOC 5 to 300 milligrams per liter. Surface less than 10, icy 200. Surface waters greater than 10, 200 IC in the milligrams per liter. Processed water, you'll start to see lower levels. Drinking water, 1 to 5 milligrams per liter. Water for injection, and then clean in place with lowered limits. So we'll talk a little bit about the regulatory methods that are available. There are the EPA 415.3. That is a method for TOC analyses, and while it doesn't call out a particular oxidative technique, it lists out all the different ones that can be used under this. There's EPA 9060A, that is a RECRA method, and that is mostly used where you use a solids module for that. And we have a solids module that interfaces to our Aurora TOC product line. The different ISO methods, ASTM methods, one that's real big in the drinking water industries with municipalities, contract labs, is the standard method 5310B. That is combustion. And then 5310C is the heated persulfate method. And then there's other methods. And also there's a USP 643 that is available uh, in the pharmaceutical market. The 415.3 method applies to source and drinking water between zero point 0.5 and 50 ppm. Must sparge for 20 minutes for proper IC removal. This allows for combustion, UV persulfate or heated persulfate, so it is open to all the techniques. There's 5310, which mentioned, and there's the two different types for that. There's B for combustion, C for wet oxidation. This is determination of water and wastewater. From Can go from 100 ppb to 4,000 ppm per sulfate. And then also there's studies from 1 to 25 ppm for the membrane conductivity. A little more expansion on 5310B. This is the combustion method is preferential to organic carbon that could contain suspended materials. That's a better technique to break that up. In wet oxidation, you might not be able to oxidize those. It's also limitation to the technique is the magnitude and variability of the blank. Minimum concentration is 1 ppm carbon or less, though 1 ppm carbon. Um, C is highly recommended, and you can use phosphoric or sulfuric acid for the acidification. And here's 5310C. When determining the technique, this should be noted, intensity of ultraviolet light reaching the sample may be reduced by highly turbid samples or aging light source. That's with the UV lamp. With the Aurora line, we don't use a UV lamp. We do the heated oxidation technique. Some instruments can give lower results for certain difficult to oxidize compounds under certain conditions. Persulfate oxidation of organic modules is slowed in samples containing significant concentrations of chloride. In the case of that, you can increase the persulfate addition, and also you can increase the time in the chamber for oxidation. And with chloride samples, with the wet oxidation, we do have like a halide scrubber that can help scrub salts and chlorides in the sample, or whereas the CO2 is going through. So touching a little bit again back on the history of the uh, TOC analysis, we stopped with the Shimadzu gang in 1988. So here's the OI analytical history of TOC. Um, Dr. Fredericks with Texas A&M helped in conjunction with this. We developed the first total organic carbon analyzer. There was the Model 524 ampule TOC method that used a purging and sealing ampule. That was wet oxidation. Then about a year later, we came out with the Model 525 combustion TOC analyzers. So these were our very first analyzers. What was really neat is that these were going on ships, and they were made pretty large, as you can see in the size, so they could put a cinder block in there to help keep the instrument from rocking back and forth out at sea. For our current instrumentation for combustion, we operate at 680 degrees C. We use NDAR detection and a platinum catalyst. With our design, we also have a catalyst guard that goes into our combustion tube, and that acts as sort of like a sacrificial piece of glass that takes the brunt of the acids and the heat and the oxidation, where that helps preserve the life of the catalyst bed. So we have a quartz bed, catalyst, and then mesh. With high temperature combustion oxidation characteristics, you will see some higher system blanks or background due to the carbon memory effects. Humic acids, bacteria, vegetation, certain molecular weight molecules are oxidized with greater efficiency using high temperature combustion. High oxidation efficiency of high temperature combustion loses its value at lower concentrations below about 1 milligram per liter of carbon, since it's limited in sample volume compared to chemical oxidation. And then also too, for lower detection limits, a method utilizing larger sample volumes should be chosen. With the operating parameters for high temperature combustion, this method chosen minimizes sample method development to sample size, and then TIC removal. With the sample sizes, it ranges from 0.01 to 2 milliliters, and that's optimized to minimal ejection while keeping reproducible results and effects of carbon memory. Although there is opportunity for larger sample injection, there's the preference for a smaller sample injection size, This again is impact on the catalyst, the particulates, and carbon memory should be under consideration. Uh, with the operating parameters, there's TIC removal. That can be from 2 to 20 minutes, depending on the method, based on the conditions for the instrument, removal, amount of concentration of acid, room temperature versus heated, internal versus external versus online. And methods vary for TIC removal, and got these considerations to take um, in effect. And it also should be sort of incumbent upon the analyst to ensure the removal of TIC under the manufacturer's specifications. So, operating procedures in high temperature combustion analysis modes spoke of TOC by subtraction, which is TC, total carbon, minus TIC, total inorganic carbon, and TOC sparging by MPOC. Uh, TC minus IC is the analyze the TC first, then the IC. The concentration of the TIC should be relative to the concentration of TOC, and that should be taken in fact when choosing this mode. There are TOC concentrations that can be found in typical ground or surface water samples. This was run with that from these results here. NPOC mode would be remove the TIC first. Remainder detection is TOC only. Uh, Loss of volatiles is a rare occurrence. And same example of 1 ppm TOC with 100 ppm TIC with a max 2% RSD. And again, this is a mode typically run by most in the uh, combustion technique. There are some challenges, reduce maintenance costs and simplify maintenance procedures. Um, there's the combustion tube, and at some point in time will require repacking or replacement. Um, that's why with our design for our 1080 TOC, we came up with that catalyst guard to help extend that life. Also, the frequency of maintenance is dependent on several factors, such as that sample matrix, sample throughput, and the combustion tube design. Reduce maintenance costs and simplify maintenance procedures. Maintenance can take many hours in some cases. The combustion tube is not only a component that is susceptible to damage, and equal attention must be given to the combustion tube interface to the analyzer. One of the big things, again, with the with the combustion tube is that that does need to cool down before you can start to work on that. So with our 1080, this is our combustion only analyzer. You look at total cost of ownership with our proprietary design. It extends that catalyst life with mention of catalyst guard. It reduces startup time and eliminates sample delivery issues. It complies with most of the regulatory standards. Uh, it is software driven, intuitive interface, simplifies operation and reduces training requirements. Um, it was designed for ease of maintenance, very easy to get into, several screws and such to get into the side panel to get to the combustion tube, one screw to lift the top to get to your permeation tube. Here's an example where that is where the desiccant dry right tube is, and then also that is the halide scrubber that I mentioned. As the CO2 goes through both of those, we like to dry that CO2, and then ultimately that goes through the Nafion tubing with our perm tube and onto the NDR. So I like to dry out that CO2 as much as possible. There is the smart slide injector design where the combustion tube cap slides over the tube and kind of locks in position. Uh, it was designed where you don't have to replace an O-ring regularly with some other manufacturers. There's pulse time injection where we kind of spritz sample in where you don't have like a big rush of sample hitting your combustion tube at once. And we have stop flow bypass, which is an in-furnace trapping scheme where with the combustion tube cap over the tube, that acts as a CO2 trap. So again, addressing the challenges, easy access, remove, repack, reinstall combustion tube in minutes. This one side panel comes away, two set screws, undo a couple of fittings, and you can get to your combustion tube quite easily for maintenance and repair. This is the slip slide injector where it has a quick disconnect linkage to attach the actuator from the cap. Uses ramps in the slide to reduce friction. Uh, this is where we spoke about where it increases lifetime of the sealing O-ring from 30 days to 15 months. The lifetime of the slide is 18 to 24 months. And this is like shown in the inject position where it's in fully engaged on top of the combustion tube. This is the catalyst guard mentioned. It's a small sacrificial tube to protect the main tube and catalyst. It decreases your cost of frequency replacing catalyst. Feasibility testing, we did testing with this with high salt particulate samples, verified cleaning maintenance, and quantified the extended life of the catalyst with this apparatus. Here is pictures of that. So before, there's your catalyst guard, and after 4,700 injections of 40 microliters of 3% salt, that is the result afterwards. So that took all the brunt of the acidification heat and helped maintain life of the packing. With the stop flow bypass injection, this allows for larger sample volumes to be converted from liquid to steam prior to releasing the CO2. Basically turns this furnace into a CO2 trap. You get better peak shape, and then longer reaction time mitigates the effects of the carbon memory as more carbon is removed from the sample. And the pulse time injection um, allows for both large and small sample volumes to be injected more accurately into the furnace. The interval between pulse allows for the carbon in the previous pulse to fully vaporize and react with the catalyst. So here's some typical method settings in combustion mode, 0 to 100, ppm cow curve, internal sparging, sample volume, acid volume, 680 degrees C, our sparge times 1 minute, reaction times 1, detection limit is 3 minutes, and number of replicates, we have 3. And here is a calibration curve for the 1080. The linearity is well within all applicable method requirements, while covering a wide range of TOC concentration. And these are the results from calibration curve shown in the previous slide. Uh, Wanted to point out that these results are attained without the use of the outlier removal. And these are results from 3 consecutive injections of standard at each calibration point. And these are results from sequence that was used to validate the previous calibration. This is typical sample sequence. It might be used as service contract, municipal, or industrial laboratory. So continuing with that timeline, going all the way back to when TOC was originally sort of discovered and worked with, was all the way back in 1756 with Joseph Black. Invented the analytical balance and studies of carbon dioxide by measurements with loss of ignition. Westinghouse in 1924 patented a measuring device that placed steel stamps in 1000 degrees C furnace and measures cryogenically. American Cyanamid patents the IR gas analyzer. Um, Menzel and Vaccaro created an ampule-based wet chemical method to analyze seawater. And that was sort of what we had done with our first models with that purging and sealing that ampule apparatus. And the first commercial TOC analyzer developed using gas chromatography and later IR detection was in 1965. The heated persulfate technique, wet oxidation by ampule method, first reported in 1964 by Menzel and Vaccaro, and commercialized in 1965 by Oceanography International. OIC later became known as OI Analytical. The accuracy and low-level detection are advantageous of heated persulfate. Lower operating costs, lower ppb detection limits. You can go down to very low limits. People report 2 to 4 ppb, but those are typically in really pristine, clean conditions. You got to have really nice, clean reagents, DI water. But this is the instrument to do your extremely low levels. Minimal routine maintenance. You can do varying sample volumes. And there is low and consistent blanks with not much drift or carryover with this. Oxidation of organic carbon by heated persulfate is very effective. Persulfate is a very strong oxidant used in many methods other than TOC. Persulfate oxidation is easily adapted to batch analysis and use of fairly large sample volumes. Unlike UV, heat transfers throughout the sample by convection, ensuring adequate contact of organic molecules. Uh, with the oxidation technique, the heated persulfate is accomplished by the generation of hydroxyl radicals. Uh, this could be also same mechanisms for oxidation in the UV persulfate technique as well. In the first step, persulfate forms hydrogen sulfide ion, and in the reaction, the water hydroxyl ions are formed, and further reaction creates the hydroxyl radical. This is a schematic of the reaction vessel. and heater assembly that we utilize on our 1030W wet oxidation TOC analyzer. The heater element at the end of the heater assembly is submerged in the sample. Uh, the sample, acid, and persulfate enter through a side port from the syringe and multi-port valve. And then after reaction, water is removed by the condensation vessel portion of the reaction vessel. Carbon dioxide is swept through a port on the cap of the assembly through a halide scrubber and permeation tube for removal of halides and additional moisture. Um, there's no carryover, uh, no salt buildup, maintains low analytical blanks, maintains low background. There's the DI water inlet, rinse volume max, and then pressurized drain that we drain out after the reaction. With combustion, inorganic matter does not combust, will build up inside combustion analyzer, causing TOC performance to degrade and shortening life of the catalyst. That causes downtime with the heated persulfate method. It drains the solution out of the TOC after it's oxidized and purged. No salt built up forms inside this tube. And then no memory as in combustion. So these are some results of a correlation of heated persulfate. These are obtained in a round robin study for EPA 415.3 at low TOC concentrations. Techniques like the heated persulfate are the techniques of choice. This is low-level analysis of TOC in drinking water, bottled drinking water. Uh, Often asked of how our instrument does at low levels. We believe that heated persulfate analyzers are a technique of choice for low-level TOC, uh, and these results kind of show that. There's the with this, there's method interferences for heated persulfate. There could be contamination, incomplete TIC removal, incomplete oxidation of certain classes of compounds, high chloride, and there could be particular attention to good laboratory practices being employed to avoid contamination of the glassware. Operating parameters should be set for optimization of TIC removal. Other parameters can be adjusted to optimize oxidation of difficult to oxidize compounds and salt matrices, where I had mentioned you can potentially add more persulfate, increase the reaction time as well in cases of those samples. Characteristics of heated persulfate: there's multiple matrices, low detection limits, precision, accuracy, flexibility, no salt accumulation, high concentrations, lower operating cost, and minimal downtime. It's applicable to a wide variety of sample matrices. It offers detection limits that are considerably lower than the combustion technique, as well as significantly better precision and accuracy for low-level TOC samples. And so back to the timeline where we had discussed this again covers um, the development from wet oxidation and combustion. This is just a little bit more info with regards to UV persulfate. Earhart developed a TOC instrument using a Technicon auto analyzer. This method combined continuous flow, ultraviolet eradication, and persulfate oxidation and collected the CO2 generated into a dilute sodium hydroxide solution, measuring carbon by change in conductivity. Ironically, uh, we do sell a automated chemistry analyzer, and our original format from the group known as Alchem, who we purchased that line in 1996, had sort of a kind of background with this Technicon technology. And many, many, many years ago, Alchem also did have a TOC cartridge, sort of like using a conductivity measurement as well. Uh, then Cowett improved on Earhart's original procedure by optimizing pH, persulfate, concentration, UV, and IR detection. Uh, this is a generic representation of a UV persulfate oxidation vessel. Uh, The heater assembly is placed by an in situ UV lamp assembly. Elements of design may be similar to this illustration in regard to sample and a reagent injection, as well as moisture removal. In some cases, TIC removal may be accomplished in a separate vessel and transferred to the UV reaction vessel. Interferences for UV persulfate oxidation, contamination, uh, incomplete TIC removal, intensity of UV lamp reaching the sample matrix may be reduced by turbid samples, potential of high chlorides. These are some of the considerations that you have to take uh, with UV lamp. Also, you would have to replace the lamp over time. The one thing that was discussed in the standard method, their 20th edition, they did talk about how UV light must penetrate the sample for a complete reaction with the reagent. And in the case of turbid samples, they may prevent complete transmission of light through that sample, thereby reducing the oxidation capacity. And they had kind of brought that up in that version. They did ultimately remove that because I guess they're kind of possibly pointed at being a little slanted towards the uh, oxidation technique that we offer with the heated persulfate. With characteristics of UV persulfate, limited matrices, non-turbid samples, which we just discussed with turbidity, low detection limits, good precision accuracy. It's not recommended for salt samples, narrow dynamic range as compared to heated persulfate. And as mentioned, you have to replace that UV lamp, so you do have some cost with replacing that. Now we'll touch on carbon dioxide detectors. Uh, there are three choices with carbon dioxide detectors. There's non-dispersive infrared detector, conductivity, or membrane conductivity. With a non-dispersive detectors, it utilizes IR radiation to detect presence of carbon dioxide. The IR beam is transferred through a chamber while the carbon dioxide in the carrier gas stream flows through that. Carbon dioxide measurement is a function of the absorption of IR in accordance with Beer's law as it travels through the flow cell. Concentration measurements are based on the difference in the IR absorbance between a reference and an analyte signal, reference and analyze sample channels, measure carbon dioxide in a single path through use of narrow band optical filters with appropriately selected bands. Concentration of the carbon dioxide present in the optical path will result in reduction of IR intensity as it traverses the flow cell. This is an example of a UV persulfate with membrane conductivity detection, and this has a lot going on here. This is the flow path of this apparatus. Uh, as alluded earlier, some techniques must use TOC by subtraction methodology for TOC determination. This is the technique that does that. So the basic mechanisms for TIC removal by acidification, oxidation of organics with UV light, and persulfate are the same as in other techniques. What is different that at each reaction step has its own conductivity detector for that. Carbon dioxide is generated in the oxidation step, changes the conductivity of the deionized water. The change in the conductivity is related to the carbon concentration in the oxidized sample. The membrane in the membrane module is a CO2 selective fluoropolymer that is hydrophobic and non-porous. The relationship between conductivity measurement and carbon concentration is described by a set of chemometric equations for the chemical equilibrium of carbon dioxide, bicarbonate ion, and hydrogen ion, and the relationship between the ionic concentrations and conductivity. So again, a lot going on in this chamber. Uh, Condometric TOC basic principle. Uh, these uh, this technique shares many of the attributes as well as the difficulties associated with other techniques um, that particularly well suited for high purity or ultra pure waters with relatively low TOC concentrations with the condometric TOC. The potential for positive interferences due to membrane crossover must also be considered with this technique here. Also, there could be anything with regards to sample with particulates. High turbidity will be impacted with this principle. So characteristics of UV persulfate oxidation: reasonable oxidation of organics within limited range, uses no carrier gas, thus has influences from other species than TOC, calibration of the conductivity detector as little as once a year, low system blanks, relatively slow sample turnaround, TC and IC, uh, good precision at ppb levels, but poor accuracy, TIC minus IC. I mentioned again the interference with chlorides, conversion to chlorine, and potential interference or membrane crossover by sodium, potassium, ozone, chlorine, temperature, and pH. You can get false positives or negatives. So in conclusion, the three techniques that are available today is the high temperature combustion, oxidation, heated persulfate, NDAR, and UV persulfate, NDAR conductivity. All techniques are adequately governed by regulatory methods. No single technique is optimal for every application. However, operational parameters can be adjusted as needed. So the results would meet the criteria of a particular regulatory method or error of measurement. The ultimate choice of a technique may be dictated by ease of use, cost of ownership, or standard operation procedure requirements. Uh, that concludes presentation. So if there's any questions, could take those.
Pessoal, alguém tem alguma dúvida? Pode escrever no chat que a gente pergunta para o Henk, caso eu não queira perguntar em inglês, tá bom? Vem aqui explicar. Tenho uma dúvida. Super crítico.
Oh, and I see a question about the supercritical technique. I am not familiar with that, but let me take a note and check with application chemist with that. TOC, super critical technique. And then what I can find out, I can pass through Nova here, and they can forward that on. Correct. Is there any